I'm Anil Kumar sharing with you some practice questions on forming differential equations from given functions. So we have four functions here, right? The equation is form differential equations representing family of curves. As you know, differential equations actually represent family of curves and their solutions are always functions, not just points, right? So we have four very similar type, but you will see how the approach can be very different in making a differential equation from the function. The first step is to check the number of parameters. So what we do here is we try to figure out how many parameters are there. So sometimes we say parameters and sometimes we say arbitrary constants. Now, in the first equation, we have only one arbitrary constant, which is c. In the second equation, we have two, a and b, right? So in the first equation, it is c. In the second equation, it is a and b. In the third equation, we have only one, which is c. And then again, we have just c. Now, what does that give you? Arbitrary constants give you an idea of the order of your differential equation, right? So now we can say what is order of our ordinary differential equation, right? So we are working with ordinary differential equations. That means we are differentiating with respect to only one independent variable. So order is same as the number of parameters. So order is 1 here, 2 here, and 1 for the other two. Correct. So that is the first thing. Whenever you look at a differential equation, you have to understand how many times should you be differentiating the equation to get the result. And now the idea is basically to eliminate arbitrary constant. So once you eliminate arbitrary constant, what you get is your ordinary differential equation. Correct? So these are the steps involved. Let's take them one by one. You can always pause the video, copy this question, try to do them, and then look into my suggestions. So now here's the first one for us, which is we need to form the differential equation representing y equals to c times x minus c whole square, correct? Now there is one arbitrary constant c, so we should be only differentiating it once. So we have our equation as y equals to c times x minus c whole square. So when you differentiate, you get y prime equals to, now 2 times c, right, x minus c. This is what you get once you differentiate it with respect to independent variable x. So we differentiate with respect to x. So we get this. Now, how can we eliminate c from these two equations? So we have two equations to work with, right? So let's call them as equation 1 and 2. Now, as you can see, if I divide 1 by 2, I'm able to eliminate c. So the next step is we'll divide equation 1 by equation 2. Is it okay? So what we get here is y over y prime, that is dy dx, right, equals 2. So c and c cancel. So we get x minus c in the numerator, right, and we get over 2, correct? Now from this equation we can isolate c. That's the whole idea. So we can isolate c. So we can cross multiply. So if I cross multiply, I get 2 times y over y prime is equals to x minus c, or we get c equals to x plus 2y over y prime. Correct? So in a way, we know what c is, and this c can be substituted back into the equation, and that is how we can actually eliminate c from the whole equation. You get an idea. So this is the basic concept to work with. Is it okay? Correct? So let's do it on the right side now. So we call this as our equation number 3. So we are going to sub 3 in equation 1. Correct? Get y equals to, instead of c, I'm writing x plus 2y over first derivative, right? So that gets into the bracket, and the second bracket here is x minus all this, right? Which is x, and I'll take minus of this, minus 2y over the first derivative whole square. Now clearly we get x plus 2y over y prime, and here x and x cancel, so we have minus of 2y over y prime, the first derivative, whole square. Okay? Now we can take this as a common denominator, so we get y prime, x times y prime plus 2y, and here it becomes positive 4y square over y prime, first derivative, square. When you square, you get square. So you get y prime cube in the denominator. Okay, so let's rearrange. So we have y prime cube in the denominator, and here we have 4 times x y square y prime plus 4 times 2 is 8 y cube. Okay, 8y cube. Now we can actually cross multiply. Here we have y here, so we can cross multiply. So we get the third order equation in first order equation, third degree, dividing by y, or I could have actually first take y common. So we can take 4y common. In that case we get x y prime plus 2y square. Is it okay? Over y dash cube. So when you cross multiply, y and y cancel. So what you get here is 4 times x y prime plus 2y square. Is it okay? So that is what you get, and that becomes your equation in differential equation. You could actually take y common, so you could also write this as third degree. So you could take 4y common, right? And you could write x y dash plus 2y. So that is a differential equation which represents a family of curve given by the equation y equals to c times x minus c whole square. Correct? So I hope the steps are absolutely clear to you. The idea is that you have to isolate c, and once you do that, you substitute it back into the equation and get the result. Let's take up the next example now. Now the second example here is form differential equation representing y square equals to a times b plus x times b minus x. Let's rewrite this equation as y square equals to a times b plus x times b minus x is b square minus x square. Correct? Now since there are two parameters here, or arbitrary constants, we'll differentiate it twice to eliminate both these constants. Correct? So first time when you differentiate y square with respect to x, so let's differentiate with respect to x. What do you get? You get 2y dy dx, which I'll prefer to write in this notation, equals to, here we get minus 2x, right? So minus 2a is already there, minus 2ax. So that is what you get after first derivative. Now, it is a good idea to rearrange and then differentiate. So this is a slightly different strategy. Normally, you will do the second derivative, eliminate a, but here what we will do, we'll rearrange to eliminate it, right? So you could actually first write this equation as y prime is equals to minus ax. Now since we want to eliminate a, I'll take x to this side. So what we get here is y over x, y prime is equals to minus a. Do you see that? And now we are going to differentiate with respect to x. So this avoids the strategy of finding a, substituting, and then dealing with the equation. So if I find derivative now, right side derivative will be 0, and we would have eliminated the term with arbitrary constant. Do you see that? So on the left side, we'll apply the product rule. So we'll do it in a couple of steps. We say derivative of y over x times y derivative plus y over x times derivative of y, which is second derivative, equals to 0. Do you get the idea? Correct? So this is a very good step to solve such equations. Now what is derivative of y over x? We can apply the quotient rule, correct? So what we get here is x squared, derivative of y, which is y prime, x minus derivative of x, which is 1, times y, and everything multiplied by the first derivative plus y over x times second derivative equals to 0. You get the idea, right? So we could get an equation in this form. Perfect. Now you can actually rearrange, correct, and get the answer. So we'll multiply by x squared all the terms, so get rid of this denominator. So when you do that and multiply by y dash here, we get y dash square times x minus y times y prime plus y times x times second derivative equals to 0. So we get our term as y times x times second derivative, and this is plus x y prime square minus y prime equals to 0. So that becomes our differential equation representing the given family of curves. You may like to rearrange this equation, taking x common, writing this on the right side. So let me do that and write down the final differential equation. So what we can do here is that we can take x common. So we get y second derivative plus derivative squared, and we can take this to the right side, which is y prime, correct? So that is how you would actually write your answer, by rearranging it and taking x common. So either way, both are kind of correct differential equations representing the family of curves shown here. Thank you. Now here is the third example. We need to form differential equation representing y square equals to x minus c whole cube. Now we'll talk about another strategy while we form the differential equation now. The given family of curve is y square equals to x minus c whole cube. Since there is only one parameter, we have to differentiate only one to isolate, correct? So if I differentiate now with respect to x, what do I get? I get 2y prime equals to 3 times x minus c whole square times derivative of inside, which is 1. So that's what I get. Now the idea is that I have to eliminate x minus c. Rather, I have to eliminate only c, right? How can I do that? Well, what I can do is I can actually take cube of the second equation, right? This equation. So let me call the first one as equation number 1. Now we have equation number 2. So if I cube equation number 2, what happens? So what I'm trying to do here is kind of like this. I'll do 2y times y dash whole cube equals to 3 times x minus c square whole cube. So what we get here is 8y cube, y dash cube, that's the derivative. 3 cube is 27, x minus c to the power of 6. Do you see that? So we get our equation number 3, which can help us eliminate c altogether. So if I do now equation 3 divided by equation 1, what do I get? So I'm dividing these two. So we have 8y squared, 8y cube over y dash square. So if I divide by y square, I get 8y y prime cube, correct? On the other hand, I have 27, the number, and x minus c to the power of 6 divided by that term will give us x minus c. 6 minus 3 is 3. Do you get an idea? I could write x minus c whole cube as y square. So I'll replace this by y square. So we get 8y y dash cube equals to 27y squared. Correct? So I substituted back equation 1, the value of x minus c. Do you get an idea? So whole cube, right? So that was y squared. So we substitute that. Now we have an equation in which we really do not have any arbitrary constant. Correct? And we can now write our final answer as 8 times y and y can cancel. So we have 8 times y prime cube equals to 27y, correct? So one of the y's get cancelled. So we get our equation which is independent of any arbitrary constant, and therefore it is a required differential equation. Now since there was one arbitrary constant, we have order of 1, however the degree is 3 for us. So we have order 1, degree 3 in this particular case. So I hope the steps are absolutely clear. You may adopt strategies like this to simplify your equations. Let's move on to the next example now. Now here is the last example from our set. We'll look into forming differential equation represented by c times y plus c whole square equals to x cube. So the given equation is c times y plus c whole square equals to x cube. Number of parameters are just 1, so we are allowed to differentiate it only once to eliminate c and then get the differential equation, right? So we'll differentiate with respect to x both sides. C is a constant. So what we get here on the left side is 2 times c y plus c, and derivative of inside term is dy dx, which I'm writing as y prime, and on the right side we get 3x squared. So we get our second equation, right? So we have equation 1 and equation 2. To eliminate c, I can divide one equation by the other. So in first step, let's do division of one by the other to eliminate c. So what we get here is y plus c, and in the denominator we get 2 y prime equals to x over 3, correct? So that is what we get in this particular case. So we have eliminated c, however we still have c in our equation. We have to eliminate that also, correct? So to eliminate this, we can cross multiply and then take away y. So we can now write y plus c as equals to 2xy prime over 3, or we can say c is equals to 2xy prime over 3 minus y. So we have a value of c now. So we can substitute this value of c back into the original equation to get the required differential equation. So let's put it back here and then see what do we get. So c is 2xy prime over 3 minus y. So we'll write it here first. So we have 2xy prime over 3 minus y. The second term here is y plus c, which is 2xy prime over 3 minus y whole square equals to x cubed. Correct? Now we can take common denominator. Here y and y minus gets cancelled. So we get here 2xy prime minus 3y over 3, and y cancel. So we have 2xy prime over 3 whole square equals to x cubed. Now that gives us 2xy prime minus 3y over 3, and this is times 4 x squared y prime squared over 9 equals to x cubed. So that gives you 9 times 3 is 27, which we can take on the right side. So what we get here is, we'll multiply this with this, all these terms. So what we get here is 4 times 2 is 8 x cubed y prime cube, right? When you multiply this with that, minus 4 times 3 is 12 x squared y prime squared equals to 27 times x cubed. Correct? So when you multiply this term, 4 times 2 x cubed, this, now all this. So x squared is common, so you can simplify this. So we can write here 8. So x squared can be divided throughout. So we get x y prime cube minus 12 y prime equals to 27x. Now you can bring the x's together and that terms on this side. So we get 8 y prime cube minus 27, right? So all this is with x, and we'll take that term to the right side, 12y prime. Correct? So that is an equation. This is a differential equation which does not have your arbitrary constant. So that is representing the given function. Correct? So that could be one way of writing it. So that will be our answer for the time being. Anyway, what you have seen in this particular set of videos is we took most of them with one arbitrary constant, except for one we had two arbitrary constants. Number of times you have to differentiate the equation to get ordinary differential equation really depends on the number of parameters or number of arbitrary constants. Once you differentiated those many times, you have to ensure that the constants are eliminated. And we have to adopt different kinds of strategies to do so. Once they're eliminated, you arrive at the differential equation which represents the family of curves of that function. So these are the steps to be followed to always create a differential equation representing a family of curves. So I hope that makes sense. Feel free to write your comment, share your views, and if you like and subscribe, it'll be great for me. Thank you and all the best.